This is requirement 2A of the radio merit badge. How does radio get from one place to another? How does it get to receivers locally? How does it get to receivers at great distances? Now that we've explored and defined some of the terms of HF and VHF and so on and so forth from our study of the electromagnetic spectrum, now we're in a position to understand how these waves actually behave. How do they get from one place to another? HF refers to high frequency, and those are the frequencies between 3 megahertz or 3 million hertz and 30 megahertz or 30 million hertz. VHF goes from 30 megahertz to 300 megahertz. Again, we will be talking on a frequency that's almost right in the middle of the VHF group of frequencies. We will be talking on 146 megahertz later on. So let's explore how radio waves actually propagate from an antenna to a receiver. The ionospheric layer of the atmosphere, the ionosphere, plays a major role for these particular groups of frequencies, the HF and VHF groups of frequencies. This ionosphere, and of course you have, for the Earth's surface, just to review, from the Earth's surface you have the Earth, and then going up into the air you've got the troposphere, which is what we're living in. Then there's the stratosphere, and then above that is the ionosphere. The ionosphere extends up about 300 miles above the Earth's surface, so it goes up quite far. So the ionosphere has several different layers of charged particles, charged air molecules. These are referred to as the D, E, F1, and F2 layers as you go from lowest to highest in the ionosphere. So the ionosphere is the first thing we need to be mindful of. The next thing is the sun. The sun's ionizing radiation, the UV coming from the sun, fragments and turns the molecules, the air molecules in the ionosphere into ions. That's where it gets its name from, the ionosphere. The more intense the sun's radiation, the deeper the ionization occurs, the deeper the fragmentation of the molecules occurs in the ionosphere. The lowest ionized layer acts like a sealing mirror to radio signals below 50 megahertz. So what happens is these signals, once they're transmitted, get reflected or repelled by the lowest ion layer in the ionosphere. And that height of the lowest ion layer varies. During the day, it's very, very low. And as the sun goes to the other side of the Earth, it rises considerably. So daytime, there's a very low ion ceiling when the sun is overhead. At night, it rises. Daytime, you have short skip distances. You have very short transmitting distances and reception distances. At nighttime, the ion ceiling rises quite a bit. You've got quite a bit of distance on your signals. Graphically, this is what it looks like. If you're in New York City and you're sending out a signal, what you're doing is you're bouncing that signal off the ionosphere. Some signals will radiate right through, will go right through, propagate right through the ionosphere. But if they are at a particular critical angle, they will actually bounce off the ionosphere, a layer in the ionosphere, and they will land quite a bit of distance away from your transmitting site. Between your transmitter and where these signals are out actually reaching back to Earth is called the skip zone. For instance, if you're sitting in New York City and you want to talk to Chicago, depending on the time of day, you might have success on a particular frequency. At night, you're almost assured to be able to talk to Chicago because this layer will have risen. So this is a depiction of the actual layers of the ionosphere. The D layer is the lowest layer here, and that's the one closest to the Earth. The D and E layers at night disappear, and the F1 and F2 combine. So at night, what you have is you've got a very, very high ceiling, so you can actually talk on HF and low VHF frequencies to the other side of the Earth. It's very, very, very exciting, actually. A lot of times a signal will bounce between the Earth, an Earth station, the ionosphere, back to Earth again, back to the ionosphere, and it will propagate like this around the Earth. It doesn't necessarily have to be a single shot. So here again, there's a couple other things going on here as well. You've got your sky wave, which is what we've been talking about, where you're bouncing off a layer in the ionosphere. You have a ground wave, which means that you've got a local station you can hear just without any interaction of the ionosphere at all. You just hear the signal because the signal is so strong, it's local. The skip distance between where you're transmitting and the signal is received again back on Earth through bouncing off the ionosphere. And of course, we call the local transmissions, local transmissions. Distant stations are referred to as DX stations. We'll talk about these two stations later on in another requirement, but WWVH and WWV are two stations that we actually can listen to determine, are we hearing Hawaii? Are we hearing Colorado? How's our propagation from those locations back to Pennsylvania at a particular type of day or any day in the week? So that's how HF and low VHF signals propagate. The higher in frequency you go to upper VHF and UHF, those signals have a much higher energy content. They are not easily reflected off of the layers in the ionosphere, so they will go right through the ionosphere. So this is why we're so successful using satellites and communicating with space modules and space satellites and so on higher frequencies, because we're not impeded by the barrier of the ionosphere. So higher VHF and UHF signals penetrate the ionosphere, and they are able to go right through. Here's an interesting link down here, hamradiosecrets.com, on how ionospheric propagation actually works. It's worth a look, and it's worth a listen. So, as we said, we wouldn't have GPS or space communications if we were impeded by the ionosphere. So one last thing we wanted to bring up here is something that's not in your Radio Merit Badge book, but it's something that is very, very important currently, and that is the role that sunspots play. Sunspots are radio's best friend, especially a ham radio's best friend for propagation. The ionization from the sun is actually coming from the sunspot storms on the surface of the sun. Every 11 years, there's a huge increase in the number of sunspots on the sun. This year, we are nearing a high number. It's called the solar flux, which is the actual radiation that's coming from the sun. And we're reaching a sunspot peak, or the peak of a sunspot cycle. And as the sunspot cycle peaks, we are able to get a lot of ionization in the ionosphere, and we are able to communicate over great distances with very, very, very little power. Again, there is another link down here that you want to take a look at for further information. And that includes our requirement of 2A on radio propagation. The next requirements are 2B, 2C, and 2D.